Okay. Good afternoon, everyone. I'm Natarajan Meghanathan from Jackson State University in Mississippi. The talk today is going to be on trying to track a mobile target moving around a wireless sensor network using Eigenvector Centrality. So this topic kind of combines ideas from sensor networks and also network science, which is like graph theory based area. So since you're dealing with, say, eigenvector centrality, which is one of the major centrality metrics in network science used for complex network analysis, let me just introduce centrality metrics and then we'll go more detail into the topic. So centrality metrics quantify the topological importance of nodes in a network. So for example, if we have network here means basically a graph with nodes and edges. So if you look at this graph here, some nodes are more important compared to the other nodes. For example, these two nodes X and Z have a larger what is called the degree, which is the number of neighbors compared to the other nodes out there. On the other hand, this node Y is kind of connecting these two, we can say, components, because if you remove this node Y and the two edges associated with it, the whole graph is going to get broken into two components. There are different metrics that capture these things. X and Z have a larger degree. So their importance could be captured using what is called neighborhood-based metrics, which is basically the number of neighbors and the properties of these neighbors, which is what is going to be captured using degree and eigenvector centrality. And nodes like Y could be captured using shortest path-based metrics, such as betweenness centrality, like Y is in between two components. So all communication between these three vertices and these three vertices have to go through Y. And closeness centrality is a measure of how close is a vertex to the other vertices in the network. So degree centrality, again, could be computed for both weighted and unweighted graphs. So in a weighted graph, first of all, in an unweighted graph, the degree centrality is simply the number of neighbors of a node. On the other hand, for a weighted graph, the degree centrality of a node would be just the sum of the edge weights of the edges incident on that node. So if you make all these edge weights as one, that's the undirected graph. So the sum of the edge weights is still the degree of the node. Now, eigenvector centrality, unlike degree centrality, not only considers the number of neighbors of a node, it also considers the degrees of its neighbors. Okay, how is it computed? It is computed using what is called the spectral analysis approach, and a lot of algorithms are out there, and we will be using this power iteration method to compute the eigenvector centralities of the vertices. And this is a theta of V cube time complexity algorithm, where V is the number of vertices. So when we do the spectral analysis of a graph, we'll be getting the eigenvectors and eigenvalues. The number of so each eigenvector will be associated with an eigenvalue, and the number of eigenvalues and the corresponding eigenvectors correspond to the number of vertices in the graph. So let me go through an example. Now, okay, yeah. So the definition of eigenvector centrality is among all those eigenvectors, the principal eigenvector, which is the eigenvector corresponding to the largest eigenvalue, is called the principal eigenvector, and the corresponding eigenvalue is called the principal eigenvalue. So the entries in the principal eigenvector correspond to the eigenvector centralities of the vertices. So let me go through this example to illustrate how we compute the eigenvector centrality of the vertices in a graph using this power iteration method. So this is a small graph. So we go through a series of iterations. The number of iterations correspond to the number of vertices. We could stop earlier, so I'll show you a kind of an optimization strategy when we could stop earlier instead of going through the number of iterations corresponding to the number of vertices. For each iteration, we need to start with the adjacency matrix of the graph. Again, an adjacency matrix of a graph is a square matrix like this. You have 5 vertices, so you have a 5 by 5 matrix, where entry is a 0 if there's no edge between two vertices, and then entry is a 1 if there's an edge between the corresponding vertices. Now, we could compute eigenvector centrality also for a weighted graph, where the entries will be the edge weights, basically. And since in an unweighted graph or the edge weights are 1, we just indicate 0 and 1 as the entries in the adjacency matrix. Now, for the first iteration, we start with a unit vector of all ones, and we are going to recompute or update this unit vector, and this is going to be eventually our principal eigenvector. With this power iteration method, we cannot compute all the eigenvectors of the graph. We are going to just compute the principal eigenvector because that's what we need for this analysis. We don't need the other eigenvectors. So we'll start with this unit eigenvector, unit vector as a tentative eigenvector that we're targeting for. And what we'll be doing in each iteration is simply matrix multiplication. Multiply this square matrix with this unit vector. And so the resulting product matrix will also be a unit vector. And as everybody knows the matrix multiplication. So for getting an entry, say 1 here, which is in the first row and it's only one column, you have to multiply the entries in the first row and this column. And that will be a 1. And then for this entry, the second row, first column. So multiply the entries here, second row with this column. Add up all the intermediate product values you're getting, and that will be our unit vector, product unit vector. The product vector, not unit vector, it's no more, it's just a product vector. Now, what we'll do is, we will kind of compute what is called the normalized value of this product vector. So how we get the normalized value of this product vector is, you just first find the sum of the squares of the entries in this vector, and then take the square root of the sum of the squares. So it'll be like 1 square plus 2 square, which is 5, plus 2 square, which is 9, and then plus 3 square, which is like 18, and then plus 2 square is going to be like 22. So then you take a square root of 22, you get around 4.69. And then what you do is divide each of these entries by this normalized value, which is 4.69. So again, the normalized value is the square root of the sum of the squares of the entries in this product vector. So when we do that, all the values are now going to be in the range of 0 to 1. So the larger value will, of course, correspondingly have a larger entry here, and the smaller value will have correspondingly smaller entry here. So for the next iteration, what we'll do is, we'll again start with the adjacency matrix. Now, instead of that unit vector, we will now work with this final vector that we got at the end of the previous iteration. So this is the vector we have. And again, we go to this multiplication, and we get now product vector. And we again compute the normalized value for this product vector by computing the square root of the sum of the squares of the entries here. And then divide each entry here again by this normalized value, which is 2.19 now. And we get now this vector. So we continue the iterations. Again, we can continue as large as the number of vertices. In this case, our 5 vertices, we could go for 5 iterations. But what we could also do is, we could see when the normalized value is kind of converging. So I just consider 2 decimal places. So in the third and fourth iterations, the normalized value I get is 2.21, which is the same in both iterations 3 and 4. So I could stop at the end of the 4th iteration, and the eigenvector that I get after dividing the entries here by the normalized value. Again, that's the final vector that we get at the end of an iteration. So the 4th iteration, when we do this multiplication, we get this product vector. And again, we compute the normalized value of this product vector that comes to be 2.21. And then you divide each entry here by this 2.21, we get this entry here. And that's going to be our principal eigenvector of this graph. And as I said, the eigenvector centrality of the vertices correspond to the entries in the principal eigenvector. So this entry 0.176 correspond to vector node 1, and 0.352 is corresponding to node 2, and so on. So the node that has the largest value here is considered to be the one that has the largest eigenvector centrality, and vice versa. So if you look at these entries here, the node 4 has the largest eigenvector centrality of 0.616. That's because node 4 has the larger degree. Again, if you go to the definition of eigenvector centrality, is a measure of the degree of the nodes as well as the degree of its neighbors. So node 4 has the larger degree, as well as its neighbors 3 and 5 have a degree of 2. And then, of course, the other neighbor has a degree of also 2. So all the 3 neighbors have degree 2, and node 4 has a large degree 3, which is the largest degree in this graph. Whereas if you look at, say, for example, let us compare nodes 2 and 3. So nodes 2 and 3 both have a degree of 2. Okay, so based on the basis of degree centrality, we will not be able to distinguish between nodes 2 and 3. But on the basis of eigenvector centrality, we could distinguish nodes 2 and 3. And we see node 3 has a relatively larger eigenvector centrality of 0.484, and node 2 has a smaller value of 0.352. It is relatively compared to node 3. That's because node 3 has node 4, which is a high degree neighbor, a node, as well as node 5, which is having a degree of 2. On the other hand, node 2, of course, has node 4, which is the same neighbor as node 4, node 3, whereas the other neighbor that node 2 has is node 1, which has a smaller degree. So the eigenvector centrality is able to capture both the degree of that node as well as the degrees of its neighbors. And then, so one use of eigenvector centrality compared to degree centrality is you can break the ties among nodes that have the same degree centrality using the eigenvector centrality approach. Of course, node 1 has a lower degree, and its other neighbor, its only neighbor, also has degree 2 only, not degree 3. Which is the maximum degree in this graph. So node 1 has the smallest of the eigenvector centrality. So that's the idea behind eigenvector centrality. And as I said, we could use or compute the eigenvector centrality even for weighted graphs. And the entries in the eigenvector centrality will then correspond to the weight of the edges in the graph. And that's what we'll be actually doing in this research too. So at that time, we'll look at a weighted graph. So let us now move on into the problem that we are analyzing here. So what we have here is a sensor network. So I'm showing an example network here. So this is of dimensions 100 meters, say by 100 meters. And we have a mobile target, which could be, say, and we are also kind of designing this for a particular domain, which is kind of a radioactive, to track a radioactive device. Somebody is carrying a radioactive device in their hand and moving around in a sensor network, and we want to track what you call the trajectory. Trajectory means the kind of the path and everything that they're taking to move around the network. Using the signals that are emanating from coming out from that device. So we'll call the device as radioactive dispersal device. So we'll call it as RDD, or we'll refer to it as RDD. So the signals emanated from this RDD are going to be captured by the sensor nodes. So if the RDD is within the neighborhood of some sensor nodes, those sensor nodes are going to be capturing the signal strength of captured by those sensor nodes are going to be relatively larger compared to the nodes around which the RDD is not there. And we are now then going to build an adjacency matrix based on the signal strength and compute the eigenvector centrality of the sensor nodes. And the sensor nodes that have a larger eigenvector centrality are essentially going to be the ones that are around the RDD. And then we are going to be going to predict the location of the RDD over time. So that's the kind of the overall nutshell. And don't get lost if you didn't get what I said just now. And we're going to go through all these things as a sequence of things. Okay. So at the end, what we really want to do is kind of build a profile for the RDD movement. So if this is the actual mobility profile of the RDD, with time, it may start from some location which is not clear here, but then move around, and then over time, it is at different locations. So what we want to be able to build is, again, so it's clear here, it's starting from this point probably and then moving around and then stopping here. So we want to be able to build a profile that is matching as close as possible to the actual profile. So that's the whole purpose here, or the objective of this research. So let me now kind of give a small background information about sensor networks, the data gathering process, and then move on and put everything together. So sensor networks are used for various applications, and one application that they are commonly used for is for environment monitoring. So for example, you want to find out the temperature of a region, or the pressure, humidity, and so on. So like here, we want to kind of see whether there's any radioactive device moving around in a network or not. If it is moving around, what path it is taking. So sensor nodes are capable of sensing the environment, and they are battery operated, so they cannot sense, one sensor node cannot sense the entire network. So we typically have a number of sensor nodes deployed in a network. And there's also what is called a control center, or the sink, to which the sensor nodes will forward all their sense data. Sometimes the sensor nodes can also do some small processing, which is also what we're going to assume in this research that they can do. And instead of each sensor node forwarding the data on their own, through kind of a long range transmission, because as you can see in this network here, each sensor node is a different location, and wherever you deploy the sink, it is going to be like some sensor node is closer to the sink and some is farther away from the sink. So some sensor nodes are eventually going to spend more energy for transmitting over a longer distance. So we don't do like that. We typically have what is called a data gathering process. And there are again different topologies for data gathering. And one common topology that is used for data gathering is a tree topology. So basically build kind of like a spanning tree around the considering all the sensor nodes, and will again have one node as a root of that spanning tree, and then it becomes a kind of a data gathering tree, so that all the data is kind of getting gathered toward that root node. And again, the role of the root node could be rotated among the nodes, so that one node is not spending all the energy to gather and everything and then transmit to the sink. So that's the idea here, and we're going to assume that there is an algorithm that can operate for this data gathering. And the sink will typically get all the aggregated data, and based on what it gets, it can come with a decision, and then pass on some direction command to the sensor nodes to do some more things. Okay, and so that's a kind of background information about sensor nodes, sensor networks. So let us now see the assumptions and the model that we are using in this research. So again, as I said, sensor nodes have operated in a limited sensing range. The sensing range is what we use to sense the data. Then for communication purposes, for two sensor nodes to communicate, because in a data gathering tree, they have to go through like peer-to-peer communication so that the data can eventually reach the sensor node. The sensor nodes also have an transmission range. So typically the sensing range has to be at least half the transmission range. That's kind of the relation between the two. And there is some theoretical work done on this topic, where they found that for to ensure connectivity to imply coverage, so actually there should be coverage here. So for both, basically, if you want both connectivity among the sensor nodes and as well as kind of coverage across the entire network, the sensing range has to be at least half the transmission range. And so for modeling purposes, we are going to assume that the sensor nodes are the vertices in this problem research here, and then there exists an edge between two sensor nodes if the Euclidean distance between them is within a transmission range, so not the sensing range. So if the distance between the two sensor nodes is within the transmission range, we're going to assume there's a link between or edge between the two nodes. And assuming all sensor nodes are going to operate at an identical transmission range and sensing range, so it's a homogeneous network. Of course, this could be extended for a heterogeneous network where the presence of a link depends on the transmission range of the nodes. But for simplicity purposes, you're assuming here it's a homogeneous network. And the energy loss incurred at a sensor node is kind of proportional to the square of the transmission range. So if you want to transmit over a certain distance, the energy loss incurred is going to be proportional to the square of that distance. So that's why larger the transmission range, the more the energy that you lose. Then we're also going to assume that the sensor nodes could sense the radioactive signals within the radius of the sensing range. So the transmission range is for communication between the sensor nodes, and the sensing range is for the sensor node to be able to detect the sense the radioactive signals within that sensing range, and then find out how much strength the signal is. And you're going to sample the network for every time unit. So if you run, say, this is a simulation-based study also. So you're going to run, say, for 1,000 seconds. We are going to assume some sampling time period. So you're going to sample for, say, every 1 second. Of course, this is a parameter. We could change the sampling time period and study what is the impact of that on the performance of this model. So that's why I just say for every time unit, it could be 1 second or 5 seconds or 10 seconds or so on and so on. And of course, we also have, like for the number of time units. So that means if there are 10 time units, that's the sampling time period. If there are 100 time units, that's 100 is the sampling time period and so on. So time units, so the clock is again ticking for every time unit. So the for the sensing, the signal strength, we are going to assume that, so if like I show here, this is the sensor node in the blue color, and if there's an RDD, which is shown in red color here, is moving around within the sensing range of this sensor node here. So the signal strength detected by the sensor node is modeled like this. So if there is no RDD around the neighborhood of around the sensing range of sensor node, then during a particular time unit, for one time unit, the signal strength detected by a sensor node is assumed to be 1. So that's kind of like the cumulative signal strength sensed for that particular time unit. On the other hand, if there is an RDD moving around in the background within the sensing range, we assume that the RDD is going to emit some radioactive signals that will add up to the strength of the signals detected sensed by the sensor node. And for modeling purposes, you're going to assume that it's going to add one more unit to that signal strength. So the cumulative signal strength detected for that particular time unit for that sensor node is going to be 2. And then what we're going to assume is, over a period of time, again, that's our sampling time period. So for every time unit, we measure the signal strength detected by sensor node in its sensing range. And so if you are, say, sampling for every 10 time units, so that means in the first time unit, it could be like 2. Then the second time unit also could be 2. And then let us say the RDD moved out of the sensing range. Then the third time unit, the signal strength detected would be like 1. And then so on. So if the RDD still is out in the fourth time unit, it will be again 1. And then if the RDD comes back to the sensing range in the next time unit, it will be like 2 and so on. So you keep adding all those signal strength values detected within a sampling time period for each time unit, and then add up all the signal strength. And so for a particular time period, for a particular sampling time period, you could then build up what is called a weighted graph. Here the weights are with the nodes. As I said, we are sensing the signals at the nodes and keep adding the signal strength either 1 or 2, depending on whether the RDD is there or not. So over a period or sequence of time units, which will constitute one sampling time period, we could come up with numbers like this for each sensor node, depending on the presence or absence of the RDD around the sensing range of that nodes. So that's the idea here, how we build a weighted graph. we are going to have a weighted graph of the nodes. And then using this as a basis, so what will happen is actually, as I explained here, once it's time for a sample to be collected, the sensor nodes will, again, as I said, sum up all the signal strength values they have detected within that sampling time period. So when it's time to report that to the sink, again, we are assuming there's a data gathering tree built among the sensor nodes. So the data gathering tree is going to facilitate gathering the information about the signal strength gathered at each node, and then forward that information to the sink. Then the sink has this information. And using that, what the sink will be able to do is come up with this adjacency matrix. So this adjacency matrix is computed at the sink. It's a square matrix corresponding to the number of nodes. So here there are 8 nodes, so it's an 8 by 8 matrix. And the diagonal entries are 0 corresponding to the vertices. Now, the other entries depends on whether there's an edge between the 2 vertices or not, and the corresponding node weights. So for example, between 1 and 2, there is an edge, and 1 has a strength of 7, and then 2 has a strength of 10. So for the edge 1, 2, we're going to add up the strength of 1 and 2. So it's going to be 17. 1 and 3 is 7 plus 9, 16. 1 and 4 don't have an edge. So the entry here is 0. Likewise for the other vertices from 1 to between 1 and the other vertices. So that's the idea here. We used to compute this adjacency matrix, the entries for any 2 vertices. And then we go through this power iteration method, as I said earlier. So there we saw a binary adjacency matrix. So here we have now adjacency matrix with entries greater than 1. We can, of course, go through the same process, compute the, start with the unit vector and compute the product vector, and then normalize that. So this is a normalized value, and then divide each entry by the normalized value. We get the values in the range of 0 to 1, and then go through this process until the normalized vector kind of converges to a certain decimal precision. So after 6 iterations, it converges to 51.06, and we can call the vector that we end up at the end of the iteration 6 as the principal eigenvector, and the entries there could be considered as the principal as eigenvector centrality of the vertices. Now, if we try to make sense of the values here, so these are the entries, eigenvector centralities of the vertices in the corresponding to the last iteration. Vertex 1 has 0.286, vertex 2 has 0.335, and so on, and that's what I am showing here. Now let us try to analyze, compare this with what we had here. So the largest eigenvector centrality is corresponding to vertex 4, which is 0.521. And if you look at vertex 4, it has a strength sensed as 9. And its 3 neighbors, it has 3 neighbors, and its 3 neighbors have strength sensed as 10, 9, and 11. So basically, it itself has sensed a larger value. That means more likely the RDD is around its neighborhood, and also its neighbors are sensing a larger, reporting a larger strength. So we can, the idea is then to rank the vertices based on their eigenvector centrality. And we could, we came up with, choosing the top 5 nodes in the network. So ideally, we could say node 4 is the topmost vertex with the largest eigenvector centrality. So we could say the RDD is within the neighborhood of node 4, but we don't know where it is, so we could say, we cannot say it is the location of the RDD is same as the location of node 4. We could say that, but that may not be very accurate. So what we do is we pick up the top 5 nodes that has larger eigenvector centrality, which in this case will come out to be nodes 4, 7, 3, 4, 7, 3, 2, 1. So basically around the neighborhood of node 4 and its neighbors. Those are the top 5 nodes with the largest eigenvector centrality. And then what we'll do is we'll take a weighted average of their locations. And that's what I am showing here. So these are nodes 4, 7, 3, 2, 1, and the corresponding locations in this 100 by 100 graph. And these are the corresponding eigenvector centralities. So we'll take a weighted average of these eigenvectors of these locations based on the eigenvector centralities. So I'm showing here the prediction of the x coordinate and the y coordinate separately. So for the x coordinate, we consider the x coordinates of these nodes and multiply them with the corresponding eigenvector centrality, which is our weight values in the range of 0 to 1. So like 100, which is location of x coordinate of node 4 times 0.521 plus again 100 for node 7 times 0.485 plus 80 times 0.482 and so on, divide by the sum of the weights that are considered, and we get 85.5. So that 85.5 is the x coordinate of is predicted as x coordinate of the RDD. Likewise, we now do for the y coordinates, take the multiply the y coordinates of the nodes with the corresponding weights, and then divide that by sum of the node weight values, and we get 91.7. So what essentially we can predict is for that particular sampling time period, the location of the RDD is 85.5 and 91.7. And then what we could do is, at the same time at the end of the sampling time period, there'll be a particular time unit, right? So at that particular time unit, we can also find out from our mobility profile of the RDD where the RDD was actually there, okay? So in order to do such a kind of analysis, we need now to know how the RDD is moving around the network. So we are assuming that the RDD is going to move according to a certain mobility model. And the mobility model we're using is the random waypoint model, which is a very commonly used model in wireless ad hoc networks and sensor networks. So according to this random waypoint model, how a node moves is it starts, say, from a certain location at a certain time, which is randomly chosen, and then chooses a velocity to move to, again, a randomly chosen target location. The random velocity is chosen within a certain range of, say, 0 to V max. So this V max is the mobility parameter. How fast is a node, is RDD moving? So this velocity to move from this location, x1, y1 to x2, y2, will be uniform randomly chosen between 0 to V max. And once we know the locations and the velocity, we can find out the time it takes to move from T1 to T2, because we can calculate the distance, and then from there we can find the time. And so after moving to this location, the RDD again chooses a new random location to move and the new velocity to move. So it's not moving the same velocity always. It moves in a randomly chosen velocity each time it changes its direction. So that way, we can now store all this, we don't need to store every location the RDD is moving. All we need is wherever it changes its direction, we need to only store those locations, those x and y coordinates, and the corresponding time values and the velocity it uses to move from, say, one location to the next location, and so on. And using that, we can do kind of a simple math interpolation and find out at that particular end of that time sampling time period for that particular time unit where the RDD was actually there. So, for example, if the RDD moved from time from xi yi at time ti to xj yj at time tj, and our time unit corresponding to the end of the sampling time period is, say, t, that is falling between ti and tj, what we could do is something like this. It's a linear interpolation, because you're assuming, again, the RDD moves in a straight line from one location to another location. So what we find is, say, the fraction of the of this line where the t is falling under. So we are going to this x and y is what we're going to actually compute as actual location of the RDD and compare that with the predicted location. So this fraction f is going to be like from t minus ti over tj minus ti. So this f is capturing the fraction of the the distance between this point t and this ti divided by the whole time period tj minus ti. So 1 minus f is going to be the other side. And then what we can do is we can say the x coordinate is this f times this opposite coordinate xj plus 1 minus f times this opposite coordinate xi. So this is a simple analytical geometry math. Then again, likewise, the y coordinate is f times yj plus 1 minus f times yi. And that way we can say the RDD was at that particular location at the time unit t. And using our prediction approach that we saw using eigenvector centrality, we will have a predicted location. And that's how we are kind of building the actual RDD profile and the predicted RDD profile. And or after we do run the simulation for the entire time unit, we can build up the two profiles and compare them how they look like. I'll take like 5 more minutes and then I'll finish off. Okay. So then the rest of the talk is going to be about how we evaluate the performance of this model. So we use a metric called the median distance error, basically to capture how close is this predicted profile with the actual profile. So for each sampling time period, we compute the distance between the actual location and the predicted location, and take then ideally we would like this distance to be 0. Of course, it's not going to be 0 all the time. So we compute the absolute value of this distance, and that's going to be like the distance error. And we're going to record the distance error for every sampling time period and then take the median of those distance error values. And then, so that's for a particular simulation run. We're going to run several simulation runs for a particular operating condition and take the mean of those median values. And so we ran the simulations for different operating conditions, which are like, say, we vary the mobility of the RDD, like low mobility, like 2 meters per second, and moderate mobility, 5 meters per second, and then high mobility, 10 meters per second, which is that Vmax value that I was initially talking about. And then the transmission range of the sensor nodes. Again, this is a 100 meter by 100 meter sensor network. So the transmission range of the nodes is varied from 25 meter or 440 meters. So 25 meters is going to be like low to moderate density, and 40 meters like moderate to high density. And what we measured is, and also what we varied is like the energy level at the sensor nodes. Sensor nodes operate with limited energy. So we'll call that as an energy constraint scenario. That is what more typically is. But again, just to get some benchmarking, we also consider the sensor nodes have infinite energy. They don't run out of energy. So that's like operating without energy constraint. So we measured the median distance error for all these combinations of operating conditions. And that's what I'm showing as a plot here. So if you see, the overall idea of the results here is, again, the no energy constraint scenario is like a benchmark, so the energy problem is not there. So again, why their sensor nodes lose energy? Because they have to transmit their signal strength that they have recorded to the sink. So to do the transmission, they lose energy. So if they do it more frequently, if they report the signal strength more frequently, that means the sampling time period is going to be smaller. So a smaller sampling time period means the sensor nodes are going to report more frequently. Larger sampling time period means the sensor nodes are going to report less frequently. So that's what I mean by frequency of reporting. So if the sampling time period is small, we could see the distance error is also going to be relatively smaller, because we are going to be able to accurately track where the RDD is within a smaller number of few time units. Whereas if the sampling time period is larger, that means there are 200 time units, within a particular sampling period. So the RDD would have moved around a lot of sensor nodes by then. And so the eigenvector centrality that we are going to compute for sensor nodes may not be an accurate measure to rank the sensor nodes and then pick the top 5 nodes and take a weighted average of their locations and say that's the predicted location of the RDD. So the distance error is going to be larger if you operate with a larger sampling time period. So that's like a trade-off. Why I say that's a trade-off? Because if you also measure the node lifetime and network lifetime, the sensor nodes are going to lose their energy very quickly if you operate with a smaller sampling time period, because you have to frequently report. So the nodes are going to die. So the time of first node failure is what I call as a node lifetime, and the time the network gets disconnected due to repeated due to the failures of more than one node is called the network lifetime. So if you operate with a lower sampling time period, you're going to, the network lifetime is going to be smaller. Whereas if you operate at the larger sampling time period, the network lifetime and the node lifetime are going to be larger. But the trade-off is, as I showed, for all mobility values, the median distance error is going to be larger as you operate at a larger sampling time period. And the other parameter, the transmission range. So if you operate at the larger transmission range, which is the brown line, you're going to, of course, lose more energy. Whereas if you operate with a larger transmission range, as you can see here, the median distance error is going to be slightly smaller compared to operating with a smaller transmission range. So it's another trade-off. And another one more trade-off you could also see is the mobility profile. So if you operate with a smaller mover, if the RDD is moving slowly and you fix everything else, you fix, say, the transmission range, and you fix the energy constraint or no energy constraint scenario, you're going to observe that the median distance error is going to be smaller if the RDD is moving slow. If the RDD is moving faster, especially if the sampling time period is larger, the median distance error is also going to be larger. So that's kind of putting everything together. You see a lot of trade-off, and this sensor network or ad hoc network area is full of trade-off. You design a protocol, you cannot optimize everything at the same time. So I just presented here all the results that I just discussed. So I'm not going to go the results again. So as contributions of this research, what we have shown here is using centrality-based approach. We can do mobile target tracking. So that's the kind of overall contribution of this work. And we use this radioactive device as a kind of a particular domain to show this. But we could extend this analysis or approach for other scenarios. You have like a grocery store, and you want to track where things are moving around and so on. One thing that we could see from the result is, which I did not say earlier, the median distance error values that we have reported here, you can note down that they are less than half the transmission range. As I said earlier, the sensing range is considered to be half the transmission range. For 25 meters, the sensing range is like 12.5 meters. And for 40 meters, like 20 meters. So the median distance error values reported are less than the sensing range of the nodes. So what that means is if there's at least one sensor node, or if the RDD is within the sensing range of at least one sensor node, that sensor node is going to be able to detect the presence of the RDD. So this is where the validity of the model is also kind of done. So if even one sensor node is within the sensing range of the RDD, you're going with this model approach, you're going to be able to find out the presence of the RDD. And in order to deploy this for a sensor network, you don't need the sensor nodes to be sophisticated enough. We just need them to be able to differentiate the background signals from the RDD signals. So they need to be able to they need to be radioactive capable. But other than that, they just need to sense the signal strength and then add up the signal strength and report that to the sync nodes. We don't need much complex processing at the sensor node. So it's a sync node that's going to compute the eigenvector centrality and all these things, which is normally possible at a sync node. So that's the kind of the talk here about this research. Any questions?